So I want to start with two quick questions. First question, who knows this guy? Yeah, okay, I can see people raising their hands. Hopefully, someone should know him. So this is, of course, a dated picture of Johan Dahmen. Second question, who knows this paper? I see less hands being raised right now. So in this paper, Johan Dahmen introduced correlation matrices to study linear cryptanalysis, and today I want to use correlation matrices to study another property that block ciphers can have, namely invariants. So when I say invariants, I mean for now one of two things. The first possible thing is an invariant subspace, which is just an affine space of the input set, which I take to be bit strings of length n. And when you encrypt this affine set, you get the same set. So this doesn't happen for all of the keys because it's kind of a fragile property. And the keys for which it's happening are called weak keys. And the second kind of invariant is a generalization, or you can think of it as a generalization. So in this case we have a set which doesn't need to be an affine space anymore, but just any set, and it's encrypted to itself, like in the last slide. But we now also allow a second possibility, which is that the set is encrypted to its complement. And which of the two options here happens depends on what the key is. So, having introduced, or for some people we called these two attacks, these are the three problems that I'm going to talk about today. So the first problem is a bit vague. It's just the general problem of can we understand what's going on here? And I want to take a different look at this, at these properties from the point of view of correlation matrices. And then in the second part of the presentation, I'll be talking about two more practical things. First of all, in many future work sections of previous work on this topic, people have asked whether or not you can find invariants that aren't invariant for the round function. And so I'm going to answer that question in positive today. And then I will also be talking about whether or not we can attack block ciphers using invariants, even if you can arbitrarily choose the constants. This is related to some recent work presented at Crypto 2017, where people tried to show that if you pick the round constants appropriately, you can't have invariants. So for the theoretical part, I want to start by talking about how we can think about the state of a block cipher. So remember we had these sets which were supposed to be encrypted to itself. So if you have a set, you can always think of it as just a uniform probability distribution on that set. And that's just a probability mass function, so you can think of that in terms of a vector of coordinates. And if we have a set and its complement, we might want to have some sort of a nice description that as one object describes those two things. So what we could do is we could subtract two probability distributions, so we get some kind of a function that is positive on the set and then negative on the complement of the set. And again, we can represent that as a vector of coordinates. Of course, we typically want to do something with those sets. We want to encrypt them, or we want to, for instance, add a constant. That seems like the easiest operation you could do. So you have some probability distribution P, you add a constant, you get some output distribution, let's say Q. And what I will be doing mostly in this presentation is I will be using not P and Q, but I will be talking about their Fourier transformations. And by this I mean Fourier transformations with respect to this abelian group, which is this set of input bit strings, this vector space. What this really means is just that I'm changing the basis. So here on the top part, I'm thinking of these functions in terms of the delta function basis, if you wish. And then on the bottom part, I'm using another basis set of character functions. And it turns out that's useful to describe some operations. So when you look at this in terms of coordinates, on the top part, you have some permutation matrix, which are multiplying with this vector, which represents a probability distribution. And then you get the output vector. And if you take the Fourier transformation, you get, of course, another matrix, because this is just linear. And the main thing I want to say for now is that the matrix here is a diagonal matrix. And that's not a coincidence. This is because we chose the Fourier basis to represent everything.
So when you say take a Fourier transform, do you really mean that again?
Yes.
So Fourier transform with respect to what?
With respect to, so you have a function from a group to the complex numbers, which is this probability distribution. This group is an n-dimensional vector space over the finite field of order 2. And with respect to that group, you take the Fourier transformation. Okay. But if you don't know what that is, don't worry. It's not just for some people, maybe. We can do this, of course, in more generally. It doesn't have to be a constant addition. If we have any function, we get some matrix, and we get some corresponding matrix in the Fourier domain, which I'm going to call C superscript f. And that matrix I'm going to call the correlation matrix of f, because it is exactly the matrix that Johan Dahmen introduced in a different way, but you can show its equivalent. So if you have two functions and you apply them after one another, then from the way I've defined these matrices, it's immediately clear that the corresponding matrix will just be the product of the matrices for each of the functions. So let's return to our problem of trying to find invariants, right? So what we wanted to do was have a set which is mapped to itself or its complement. So in terms of these functions, suppose we have some p hat here, which is in this case the difference, well, the Fourier transformation of the difference of two probability distributions. So either it could be mapped to itself if you multiply it by the correlation matrix of the block cipher. This means set is mapped to itself, and its complement is also mapped to the complement. Well, yeah, the set itself again. And then the other possibility is that the sign changes. Then it would be the case where the set is mapped to its complement. So the complement and set sort of switch around. So if you write this down, you immediately see that this is an eigenvalue problem. So in other words, we can conclude that the invariants of a block cipher are precisely the eigenvectors of its correlation matrix. But in the paper, I'm not taking this to be a theorem. I'm taking this to be the definition of an invariant. Because if you look at this eigenvalue lambda here, it could be that this is not 1 or minus 1, but it might be some root of unity. And in that case, we do really get new interesting things. But there is a problem. We're talking about this eigenvalue problem, but these matrices are huge. These vectors are huge. So how to deal with that? So we want to use some structure somehow. So if, for instance, you have a 64-bit block cipher, like Midori 64, your state is a vector of length 2 to the 64. So that's a problem. But in Midori 64, the state is typically thought of as a 4x4 array, where every cell in this array is a 4-bit value. So suppose we have a distribution on that array, but suppose every cell is independent. That's sort of a natural thing to maybe think of. Then, of course, this probability distribution is just a product of small probability distributions. In other words, this probability distribution is a rank 1 tensor, if we think of this vector space actually as a tensor product of smaller vector spaces. And the same, of course, is true for the Fourier transformation, because that's a separable transformation. If we look at the operations in Midori 64, because now we can say something about the state, but we might also want to say something about the operations. So it's a pretty straightforward block cipher. You have some round function, it's iterated a bunch of times. And in the round function, you do 4 things. First, you apply to every cell some nonlinear function, which is called the substitution layer. Then you shuffle around those cells, that's this P. Then you have this M, which applies a linear layer to every column, a linear map that is. And then finally we add a constant, the key, and some round constants. So let's start with this addition of the constants. So if you remember the example, I said it was a diagonal matrix. So this is true in generality. And in fact, it's not just a diagonal matrix, it actually is a Kronecker product of n small 2x2 matrices. And that's not a coincidence. What this means is just that this is an operation which acts on every bit in a totally independent way. It's just addition mod 2, there's no carry or anything like that. But if you think about that, there are many other mappings that we use in this block cipher which are also mappings like that. So for the S-box layer, we apply this to every cell in a completely independent way. So we again get some 16 tensor power of a small matrix. And for the mixed column layer, it's the same thing, but on a column by column basis. So that gives us enough information to start and try to solve the actual eigenvalue problem. Right? We know what the structure is of the correlation matrices, and we also know what we're looking for, which is the solution to this eigenvalue problem. So what people usually do, well, I mean, if you translate it in terms of correlation matrices, is the first thing is this problem is really hard. So we're making the assumption that we want to find eigenvalues and eigenvectors which have independent cells. So that's what I'm writing there. And I'm also saying that all of these cells have sort of the same distribution. But we can, if we're taking the difference of distributions, we get the same sort of. And then, instead of directly finding eigenvectors for this entire function, you just try to do it for every single map that occurs in the block cipher. Which is a really strong assumption, but even with this strong assumption, you can get all the previously known invariants. So now we want to do something new. We want to go beyond that. So an easy thing to do would be to say, well, maybe we can find some u, which is mapped to a v, after one round of the cipher, and then after another round, it's mapped back to u. And in fact, I'm not going to give too much details of how you can solve this problem, but suffice to say, you can solve it. And when you solve it, you can really generate a list of all the vectors u and v up to scalar multiple that satisfy that condition. And the main thing that comes out of this, or the most interesting solution, is this one. And what's very interesting about this solution is, well, one, that it isn't known yet, and the second part is just that this vector u has only a single non-zero coordinate, which means that it is actually a basis vector in this basis of characters of the group. So you can then show that this corresponds to having a perfect linear approximation. So that means if you iterate Midori 64 with possibly modified rounds constants a million times, which is even, then there will be a perfect linear hull, which has correlation 1 or minus 1. But I said already, it's possibly with modified round constants. So if we take a look at the default Midori 64 round constants, they are listed here. So this is in hexadecimal, so every row is a different round. Then it doesn't work, unfortunately. So we get 2 to the 64 weak keys from previous work, but we don't get anything new. But let's do something funny now. Let's rotate all of these constants to the right by 1 bit. This doesn't change the efficiency or anything. And now we suddenly get 2 to the 96 weak keys due to the invariant that I listed on the previous slide. So that's just to show that the designers were kind of lucky. There were 2 bits that they could have added the constants to that would have given them 2 to the 96 weak keys, and 2 bits where, yeah, it would have been secure, well, 2 to the 64 weak keys. But you might say, well, there are lots of zeros in this, so we can fix it by putting more random constants. But it's not that easy, so if you use these constants, for instance, and now we can play like a game, try to find the pattern in these numbers, but basically, yeah, you still get 2 to the 96 weak keys. So, I've shown that it's possible to have invariants which are not invariant in the round constant, but on the other hand, it doesn't work for the real or the default constants used in Midori 64. So it would be nice to use this property to get an actual attack on the totally unmodified version of Midori 64. So that's what I'm going to do next. So this is possible, and in the paper I give 2 attacks. So the first attack is an attack on reduced round Midori 64 to 10 rounds. So there are 16 rounds in the full cipher. And this is a pretty cheap attack, so requires only 2 to the 21 chosen plaintexts. And I also apply a similar attack to another cipher, Mantis 4, which is inspired by Midori. And it's a tweakable block cipher, so instead of just a key, you also have a tweak, and because of that, the attack is no longer a weak key attack, but in fact a weak tweak attack. And this attack, yeah, it's really, in terms of plaintext, you just need 640 chosen plaintexts, and then you can completely break this. In terms of the time complexity, both of these attacks are practical, so you only need 2 to the 56 calls to your block cipher. Even though this may seem to be quite a lot, well, I mean, it's still a large number, but a feasible number. But that's actually a bit misleading, because for this type of attack, you're more interested in knowing whether or not your target is using a weak key or is using a weak tweak. And in fact, that can be done really quickly. So what I mean by that is, like in 1 second, you can recover most of the key on this laptop. It's very cheap. So how does the attack work? I'm not going to say too much about it, but the basic idea is that we find a nonlinear property for about half of the cipher, which is based on this invariant. So that means we have some Boolean function f, such that f of the input here is equal to some other Boolean function of whatever your state is there, possibly plus a constant. And the claim is then that we can extend this to a 10-round attack by combining this with integral cryptanalysis. And that works by making sure that just before round 5, we get this kind of state where, so this is a set of values actually, and this set has a property that every cell takes each possible value exactly once. Because of that, and also because f can be written as a sum of 16 smaller balanced Boolean functions, which means it's rank 1. You have this zero sum property, but f here is equal to g there, possibly plus this constant, which you sum an even number of times, so it just drops out. So you get this zero sum property. But then in practice, you also have this additional widening key addition at the end. So that doesn't give you a distinguisher, but it does give you an equation in the key. And then if you change the constants on this set, which you need to apply to get this set I2, you get different equations, and if you get enough equations, you can solve that for part of the key. So that concludes the presentation. I'm not going to repeat all of the conclusions, but I do want to say there are a lot of things that haven't been investigated yet. So in particular, there's been some talk in future work sections of maybe we can try to make this statistical somehow, so we have some property that doesn't need to be true for all of the inputs. That's actually possible, and it's part of my master's thesis work. It's also interesting to look at what happens if we have complex eigenvalues. It's related to partitioning the input set into more than just 2 parts, so not a set and a complement, but for instance 4 parts. And then the attacks on Midori and Mantis can still be improved a lot. The source code is, well, it's supposed to be there, but it's not yet there, but it will be at some point. So yeah, that's it. Yes, time for questions.
The model of computation seems to be somewhat related to quantum computers now.
So yeah, you mean by as in
you have,
you have
probability
unitary
vectors being mapped to other probability vectors.
Yeah.
And then the estimate of the eigenvalue is a really classical problem in the quantum setting. So
I noticed a similarity as well, but I think it's more of a similarity between just classical probability theory and then what I use, and then quantum computation, because it's not true that the states themselves are, let's say, fundamentally complex values somehow. We're still working with classical things in the end. You just get complex numbers because you take, well, you could, yeah, even in this paper I don't get any complex numbers mostly, but if you work on other groups you'll get automatically from the Fourier transformation complex numbers. Yeah, there's some relation, but I don't. I think it's more of the fact that there is a relation between just classical probability theory and quantum mechanics in terms of how you can describe. You can also say it's just a Markov chain, right? And you apply transition matrices to this Markov chain, except I'm doing all of that in the after taking Fourier transformations.
You're basically finding a fixed point that is very close to that. That's roughly what you're doing?
So, fixed points are an example of, well, if you take a set of fixed points, that obviously forms an invariant set.
Yeah, yeah.
But in general, you can link it to cycles. So if you have a cycle, then you can get invariance from the cycles of the permutation. So in some sense, you can say you're looking at the structure of the cycles that your permutation has. That's another way.
But taking the analogy, Shor's algorithm is essentially finding a fixed point on the map, you know? in some sense.
Yeah, I don't know.
Yeah, it's true, but
Yeah, so yeah,
It's going to be interesting maybe to look at it because it's yeah.
yeah, okay.
After your master's.
yeah. Don't be master's thesis.
Suppose you find an eigenvector that's not a unit vector. How do you transform that into finding an invariant space?
I guess you don't mean unit vector, but you mean an eigenvector which isn't necessarily corresponding to a Boolean function or a probability distribution.
Yeah.
So, in principle, well, if you have just one eigenvector, then it could still be close in some sense to a vector which is a probability distribution or or corresponds to a Boolean function. In that case, you can still use it, except it will be an approximate property. I don't do that in the paper though, but you can do it. But usually, you already know actually that the invariance will correspond to, well, if the eigenvalue is real, so 1 or minus 1, it will correspond to a Boolean function or probability distribution. Well, it just has to. So you will find some eigenspace, I guess, and then you are sure that within that eigenspace there will be at least one vector which satisfies your requirements. Yeah.
Have you tried to use that division property in your integral part, or it's a simple?
Well, I thought about it, but this is a simple integral property, right? These functions are of degree 3. Well, f is the only one that matters, of course. So if you can guarantee that this is flow degree, and then you sum over, and you have this division property of sufficiently high order, then you could also get a zero sum. But well, I didn't see an immediate improvement, but it's possible that there would be an improvement. But since the degree is already 3, and you have only 4 variables right within the cell, so. But if you do the same thing for other invariants, which you can of course do, then it might be interesting. Yes. Any other questions? All right.